You should be seeing this just before spring break, and and since spring break should be happening next week, I'd rather not get started on the discrete material, which is going to be a huge chunk of this course until after. So I'm going to put in this optional lecture, but I again, like the others, I think you probably all might be interested in this. It's a technique that we could have talked about way back in chapter 2. It also extends very nicely to 3D, as we'll see in the end. It's a very powerful visualization technique. And what it's about is how do you find contours if you're given some data and you want to get the contours, values of a variable that are constant over some space. So, for example, I mean, here's the standard one is when you look at topographical maps. Any of you, the backpackers, and have topos, what you see are the contours for different elevations on a map of the plane. Let's call that the XZ plane, and you're looking at values for different values of y equals constant. And they define one or more hopefully closed contours. And finding them is not a simple matter. This is a very lovely little algorithm we're going to talk about, but the ways that people used to do that before they had decent graphic systems that were just very, very compute intensive. It took a long, long time. So it's a very non-trivial two-dimensional application. It introduces some very interesting aspects like an algorithm that has some ambiguity built into it. And it's important for, as we said, for contour plots, but also if I give you some implicit function, f of xy equals 0 in 2 dimensions, what do the values of that look like for, say, if I said, let's make it a little more general, f of xy equals a constant. What does that function look like for different values of the constant? It may not even have any solutions. It may have one solution that's a closed curve. It may have multiple solutions. But how one gets that solution is really difficult. If I give you a function that says y is some function of x, then you can take various values of x and get corresponding values of y and figure out ways to plot that in 2D and extend that to 3D. But something like f of xy equals 0 or f of xy equals a constant, you don't know, and there's no general way for always being able to solve that problem. So this is a very interesting one. It comes up all the time, and then people say, "Oh, gee, I don't know how to do that." Let me show you how we're going to do it and the extension at the end. So here's an implicit function, and as we said, you can't always, given an x, find a y, or given a y, find an x. However, if I give you a pair, then you could test if it really satisfies that equation by just sticking them in and evaluating them. And even for very simple things, I mean, as soon as you get past something like a quadratic equation, it starts getting very difficult to solve, and you have to use numerical methods. If you give for a given y, you get an equation in x, and you'd have to use some sort of numerical method in general. So it's usually looked at as sometimes called sometimes a testing function or a membership function, because you can say, well, all of the values of x and y that when you put in you get 0 are members of a set, and all of those x, y's that do not give me 0 are not members of that set. And that's an approach we'll take later when we talk about fractals and the Mandelbrot set. Or it's simply a testing function. I can test whether x and y satisfy it, but it doesn't mean that I can solve for an x given a y or vice versa. Well, here's a simple way it arises. This is called height fields, and they appear in various forms. We've seen it, I think, before a little bit. Okay, in this formulation, I'm saying that given a plane, and now I'm letting x, y be values in over some region, usually a rectangular region, I have a function f that gives me values of z, or heights. This is again the 2.5 dimensional problem. It doesn't, because it says for each in x and y there's exactly one z that satisfies it. That, you know, 3-dimensional functions are more general than that, but this is somewhere in the middle, because generally this will describe some sort of surface for over a region in x and y, you'll get a surface in x, y, z space. Now what I want to do is just change it slightly and say, if I give you a value of z, let's say it's t, that's called the contour, or that's called the isosurface value. And then I look at the equation f of xy equals t. That's the problem we had on the last slide. Now I say find me a curve, if possible, that satisfies that, and we'll call that function g of xy with the parameter t. And those are, besides being called contours, they're called isosurface values, and the iso value is t, and we're looking for that. And that's the topo map problem. So the basic strategy looks something like this. Let me talk for a minute about the older ways, because when I was first looking here and I was looking at people solving this a long time ago, this was a problem that people at the national labs were constantly plotting data. And usually what they did is they started with some value somehow they found that satisfied that, and then an x and a y that satisfied that for a value of t, and then they try and follow the curve. They try and step a little bit and find another value that was close by changing x and y a little bit. Then it would connect the 2 points, and then they'd find another, and these things just took forever to execute, and you just watch them slowly drawing on the screen. You're going to see this is a much better algorithm. Also leads to parallelism instantly. So let's just start with the following. Suppose what I do is I sample f of x and y, just evaluate it for different values of x, y, but we're going to do it on a rectangular grid. I'm going to start with some x0, y0, and then I'm going to take equal steps in x and equal steps in y and evaluate that function. Now we're saying nothing about the particular t I want. I'm simply evaluating it, and I'm getting an array of values that are determined by how many steps I want to take in x and how many steps I want to take in y. So for the ith step in x and the ith step and the jth step in y, I have a number fij, and I'll put that into an array. So if now I give you a particular value of t, well, that value could be, if I look at a particular sample, I could see instantly whether the value of the sample is less than or equal to t, or it's greater than t. Okay, so now let's consider 4 samples. Okay, so I'm going to look at a point fij in that array, and I'm going to look at the 3 other points next to it, one to the right, one above it, and one diagonally to the right. So that's fij, fi plus 1j, fi plus 1, j plus 1, that's the diagonal point, and f of I, j plus 1. Now they define a little bitty rectangular, or if the spacing's equal, a little bitty square cell, and those are the corners of the cell, and each of those corners have a value. And we'll see a picture of that in a second. Okay, and what I'm going to do now is, for the given isosurface, I'm going to color those corners. So it's sort of a little graph problem. And I'm going to color those corners black or white, depending on whether I exceed the isosurface value, the contour value t, or I'm less than it. I don't really care what you do with equal at this point. So let's look at that. So here's a little cell, 4 corners. Here's the 4 values. Here's fij. Let's assume that for this value of t and for these values of fij plus 1, and so on, this one is less than t, this one's greater than t, this one's greater than t, and this one is greater than t. Now, so I color it this way. I color it black if it's greater than t, and white if it's less than t, and then it's equal. Do it either way. Now, what this tells me, just looking at this is a trivial amount of information, and every time I give you a different t, you can do a different coloring of the entire array. Okay. Now, but let's look at this case, because it's kind of interesting. This one, and simple. This one says, okay, look, if this point over here is less than t, which I know because I colored it white, and this one's greater than t, then somewhere along here, the contour line, that curve, the contour curve that corresponds to f of xy equals to t, has to cross. I mean, if this is a smooth in any kind of reasonable way function, you have to, if you're below a value and you're above a value, you have to go through that value to get from below to above. So somewhere that curve has to cross. Now, you could also say, well, wait a minute, it can cross multiple times. I mean, it could have a curve, and I'll see a picture of this in a second, where it can cross 3 times. It can go like this, and then, let me go back, excuse me, across, back, across again. So, and look at this, sir. On this one, what I can say is, well, it may not cross at all because both of these values are greater than t. So there may be no point along here where the function is equal to t, so the contour curve doesn't pass here. But it can also go cross twice. So it could go, say over here, it's equal to t, then it goes a little less than t, then it comes back and it crosses again. So you can say any even number of crossings would give me the same coloring, and any odd number of crossings over here would give me this coloring. So what do? Well, we picked the simplest case, and that's a principle known as Occam's razor that says if there are multiple explanations of a phenomena, then always pick the simplest interpretation. And the simplest interpretation for this one going between white and black is that you cross once, not that you cross 3 times. And that's what we're going to do. So we're going to say on this one where we go black to black, on this one we go black to black, there are no crossings of the contour curve. So what that said is that for this little bitty cell, I've got a little piece of curve going through here. I don't know what it looks like in reality, but what I can do is approximate it by a line segment that goes between these 2 points. I'll talk about computing these intersections in a few minutes. But I have a little piece of the curve that's independent of any other cell. So I can do this for every cell, and it's called marching squares because I can take the whole data array and just march through it cell by cell, getting all these little pieces of curves and putting them together at the end. So, and that obviously leads to parallelism because all of these cells are independent of each other, so that once you have this array of data values by sampling, for any value of the isosurface or contour, you just march through the array and get these little pieces of curves and then display them. So let's look at what kinds of curves we can get just from one cell. So the next question is, well, here's one coloring of the cell. How many are there? Well, you can argue very quickly there must be 16 because you have 4 corners. Each corner could be black or white, so you have 2 to the 4th or 16 different cases, and here's those 16 cases. Okay, so we'll talk about these dotted lines in a second. So here's 4 blacks. There are three. There's a lot of symmetry in here. There are 3 different ways of having 1 white and 3 blacks. So it's 4 ways. 1 for each for having exactly 1 corner white. Here's 1. Here's 2. Here's 3. And where's the 4th one? The 4th one is somewhere. Here it is. Here's the 4th one. You can also argue that you have symmetry. 1 black and 3 whites is really just symmetric to 3 whites. 3 whites and 1 black is symmetric to 3 blacks and 1 white. Now, what about the principle of Occam's razor? We're going to take the simplest interpretation for each one about how the curve would cross these edges. So we said, look, the simplest interpretation when you have 4 blacks is that the contour curve never crosses the cell, and by symmetry, this case over here of 4 whites is the same. The case where you have 1 white and 3 blacks, you have to cross this edge here, and we're going to say the simplest case is 1. You have to cross this edge, so the simplest cases are a little line segment that connects these 2 edges. Likewise, for the 3 other cases with 3 blacks and 1 white, and the 4 cases where you have 3 whites and 1 black. Because here you get no crossings, 1 crossing, 1 crossing. So you get a little. Now, that takes care of all the cases where you have all black, all white, and 1 black or 1 white. Now, you have the only other case possible is you have 2 blacks and 2 whites, and there are really two distinctly different ways of doing it when you take out the symmetry. One is right here, where the 2 blacks are on one side and the 2 whites are on the other side. That's symmetric with all cases where you rotate this, so there should be 4 cases like that. In that case, the simplest interpretation is that there's no crossings over here where the two whites are connected, no crossings where the two blacks are connected, but there has to be a crossing where white goes to black and white goes to black on the other side. So we draw it like this. And for the other cases which are symmetric, here's one of them. We draw it here. There's the third case that's symmetric, and here's the fourth case that's symmetric. Now, there are 2 cases left. If you add them all up, we've done 14 of these 16 cases. There's one more case left where you have 2 whites and 2 blacks, but the 2 whites and the 2 blacks are each diagonally opposite to each other. So here's one of those cases, and here's the other case. Now, this one has an ambiguity that I'm going to talk about in a few minutes, but notice here what the interpretation is. It says you have to have a crossing between every black and white pair. So there must be a crossing here, there must be a crossing here. So I could draw this little line segment and this little line segment similarly for here. But it turns out I could have also done it this way, and that's where the ambiguity comes in. And as I said, I'll come back and talk about that. So putting that all together, it turns out there are only 4 unique cases where all of them have the same color. Only one has one color, and the other 3 have the other color. And then 2 different cases where you have 2 blacks and 2 whites. And you could talk about the probabilities of those and that. But it means that if you're going to write a program to deal with all the cases, you're just going to map them into these 4 cases when you're writing your code. Okay. Now let's look at the ambiguity problem. I could have drawn this one with the 2 blacks and 2 whites. I could have drawn the intersections this way or the intersections this way, and given no other information, I have no reason to prefer one over the other. So that's why it's ambiguous. Now, you could argue if you had more resolution, you would be able to maybe distinguish which one was right, but you don't have more resolution. So lacking any other information, this is what people do. Well, they pick one randomly, or sometimes what they'll try and do is interpolate values on these edges and try and break an ambiguous cell up into 4 smaller cells, subdivided, and see if that doesn't remove the ambiguity. If you look in practice what that ambiguity does, here's a little region. So let's see if we try and connect those 2 different ways of drawing lines for this case with a little bit bigger region. So here's a big region, and there happens to be an ambiguity for this one, but no ambiguities for the others. So here, you get something like this and this, but now I have 2 different ways of coloring this one. If I color it this or draw the lines this way, then I get a little rectangular area here, which is, if you think in terms of topo maps, that would be a little isolated peak. The other way you do it, if you connect it instead of here to here, you connect this point to this point and this point to this point, then you get sort of this little ridge going down here. And if you've ever hiked with topo maps, there is a little bit of ambiguity in there. You only have the contours for certain values, and when you get down to that kind of resolution, you really don't know any better what's actually there on the ground, but you're pretty close. Okay, here's another little picture of that drawn with some, if I try to draw it a little bit differently, I have, 2 different ways that I drew them here as curves, but here's the same coloring in terms of the black and whites on just these 2 cells, and here's, because these are both ambiguous cells next to each other. Look at these 3 distinctly different ways I can do it. But again, if it's inherent in the problem because you just haven't sampled it at a small enough spacing to be able to resolve that. And that's the argument over here, is that it's a sampling issue. It's not something that there's this magic solution if you had picked another way of going about this. There's no right or there's no wrong here. The problem when you go to 3D is that if you compare this to the real data that you sampled and you picked the wrong interpretation because you didn't quite know what to do, it will visibly leave a hole. It could visibly leave a hole in the surface. In 2D, when you're doing this kind of thing, it's relatively harmless which choice you make of that. In 3D, it really could visually be annoying. And as I said, there are a couple of things that people do. They try and super sample. They try and look at bigger areas and put curves through them, but it's a problem. Okay, so now let's address the last issue. When I do this interpolation here, where do I actually decide the crossing is in any of these cases? Do I say the crossing is halfway between black and white? Well, that wouldn't work if depending on how far above the threshold or the contour value the black is and how much below it the white is. I'm much better off interpolating smoothly, as I'll show you in a minute, between the two. But those are the standard ways. One is to say you go halfway. The other is to try and use interpolation along this edge based on the values of the samples here. Okay, so let's look at that. Okay, so this is halfway or interpolation. And let me give you, this is a wonderful example to try. It's called the ovals of Cassini. And depending on the values of A and B, you can get no curves, you can get a single curve, as that I'm showing you here, or you can get two separate curves for that. So it's a fun function to play around with and do examples with. It's also, well, I guess you have a chance of solving this. No, you can sort of solve it for x and y because it's quadratic. Anyhow, if you use midpoint, this is what we got. I forget what the resolution was here. Maybe it was 128 by 128 or something, because I wanted to show you what you get. You know, it's kind of rough. If you interpolate, just this is, you know, essentially the same algorithm, same interpretations for each cell, and in this case, you get a very nice smooth curve joining them. You could sort of see the underlying this, the little jaggedness, because I didn't do this at a very high resolution just to demo it. So it's a very powerful technique for doing this. Here's a better example, I think. The Honolulu data, which I used to show surfaces, and I think we already had one example, and I'm going to come back to that a little bit later, use that data set. So here what I've done is do contours, a whole bunch of contours, for a small region of that data set. That data set is approximately 400 something by 400 and something. I took small area. If you've been to Honolulu, this is the Diamond Head crater. And what you do, this is giving you a little topo map. I did this repeatedly for different contour values. And now, so this is a contour that's pretty close to sea level. This is a little bit above sea level. And now you can really see the shape of the slope much more, because the contours, you know, it's very steep here because the contours are very close. So it's a very fast and very parallelizable way of doing things. So finally, I just want to mention the 3D version of this, which is called Marching Cubes. And what you're doing there is looking for isosurfaces now. So if you take a function g of x, y, and z and set that equal to some constant and say, what does that surface or multiple surfaces look like, it's the equivalent three-dimensional problem. And so what you can do now is sample it for x, y, and z, let's say equally spaced over some range. So you get cubic cells now because you're going in 3 dimensions. You also get that data kind of automatically with a lot of medical technologies. So if you look at a CT scan or an MRI scan, they're inherently going to give you digital data, so you get this volume of data. And each of these cubic cells is often called a voxel instead of a pixel, because it's a volume element instead of a picture element. And so if you apply the same argument, each of these cells has 8 vertices. They can each be colored black or white, whether they're above or below the contour value C. That gives you 2 to the 8th or 256 possible interpretations. When you take out all these symmetries, you get, I think, 15 to, there's an argument about how you do the symmetry. There's approximately 15 unique cases that all these 256 map into. And now you get, if you think in your head, I probably should have drawn one of these, of say a cube where 7 of the vertices are black and 1 of them is white, you're going to get intersections on the 3 faces close to that, around that one white cell. That's going to give you little triangles. And so you wind up generating a whole bunch of triangles. And that's wonderful, because not only is this completely parallel, but it's automatically generating triangles, and that's precisely what we're good at displaying. So this is a very, very standard and very fast method of doing isosurface visualization for volume visualization. Final note is it's kind of interesting in that if you look at the literature, you don't really find very much on marching squares because marching cubes was actually discovered first, and you wind up saying, oh, this two-dimensional problem is really a special case of this three-dimensional problem, which people have been doing for a long time in the volume visualization world. So anyhow, if you want to do some things with contours, this is very, very nice. If you're looking for projects for the term project, the 3D extension of this and looking at isosurface visualization is one possibility.